Okay, so let's get started. So I'm going to talk about Cisco ASA firewalls and more specifically a bug I found and exploited recently. So I'm Cedric. I'm working at NCC Group. I'm doing vulnerability research, exploit development, and reverse engineering. And basically, today I'm just going to talk about a vulnerability I found into Cisco ASA firewalls. And the idea was to prove remote code execution and report it to Cisco. I've been working on Cisco ASA the last year, developing tools. And when I found this bug, I was very excited because it was more and more promising, and leveraging the tools we had developed internally at NCC was a good way to prove they were useful and develop a working exploit. So what is an ASA firewall? It's basically what you have at the bottom. So it's different models. So the cheapest one is the ASA 5505, and then you have more expensive ones. But they basically all run the same software, and they are basically Linux-based, and underneath they run a single binary called Lina, and they are Intel-based, so it's either 32 or 64-bit, but they are Intel. It's important to differentiate ASA and iOS, even though they have the same kind of command line interface. They are different underneath. And an iOS is like a proprietary operating system running PowerPC. So in our case, we are only interested in Cisco ASA firewalls. And basically, they are the entry point to most enterprises because that's how you connect to the VPN to get access to your internal network or this kind of thing. So it's either you have an ASA, a Cisco ASA, or you have a Juniper or other model, but you need such a device anyway. So I'm going to talk about two network protocols that I'm interested in. The first one is SSL-VPN. It's the one that actually has the vulnerability, and you can access it for regular use using either WebVPN, using like the browser interface. So if you connect to the router using SSL, it will show up like this. Or more commonly, you may know this AnyConnect client tool, which basically allows you to connect to the VPN SSL. But underneath, it's SSL, basically. The second thing I want to talk about is iKey. So it's a completely different protocol. It's another way to establish a VPN, but in this case, it uses IPsec and iKey to establish the secure tunnel. And most of the time, it's used between two ASAs to establish either an IKV1 or IKV2 VPN-based. It's also supported, I think, by like Windows client or even AnyConnect. I see lots of places on the internet that says you can use AnyConnect to use iKey, even though I've never been able to actually have it working or actually use it this way, but it should work. So iKey, the bug is not his iKey at all, but the reason I'm talking about iKey is because I'm going to leverage iKey for the feng shui and to actually exploit the bug in SSL. There may be other way to exploit the bug, but that's the way I want to show you and show you how it's actually easy to leverage feng shui. So just previous works. In 2014, Alex Stewart was interested in looking at ASAs. He did a really good presentation. He was one of the first ones to actually look at internal routing the ASA, leaking the ASA version. It was really, really good. And then 2 years later, in 2016, Exodus Intel did an amazing job in exploiting a remote code execution bug in the iKey Cisco fragmentation protocol. Published an exploit after responsibly disclosing it to Cisco. In August, so like 4 or 5 months later, shadow brokers released exploit for ASAs as well as part of their leak, supposed to be tools used by the NSA to exploit stack overflows into the SNMP protocol. So it was a pretty tough years for ASAs, right? 2016, really to two really important exploits and available on the internet. But very interesting, and basically that was the start of the research. And in 2017, at NCC, wanted to basically see how they actually found this bug, because there isn't many tools to actually look at internals and understand how to exploit bugs and this kind of thing. So we're like, okay, that's cool. They have like working exploit, but how do they actually make it happen, right? So we basically looked at the ASA and developed a bunch of tools to analyze the memory, to have a debugging experience that is better, to unpack, repack firmwares, and we basically released 8 blog posts. So if you want to look at ASA, I really recommend you to look at these blog posts, because I'm not going to talk about that today, but it gives you like a good base to get started. So today we're going to talk about a bug in SSL. So this is the one we want to, well, not in SSL, but in a protocol embedded into SSL. And we're going to leverage IKEv1 for the feng shui in order to exploit the bug in SSL. So why does my presentation, why did I name my presentation Robin Hood? So the first thing to know when you actually buy an ASA is you can buy different devices, and if you buy a small one, it will only be able to allow you to connect up to 50 sessions. And if you buy like a more expensive one, you will be able to use 5,000 sessions. So it's like, wow, that's nice. And the interesting thing is, in IKE, you can actually have this concept of fragmentation, where you send different fragments in the same session. And the interesting thing is, if you reverse engineer the binary, you will figure out that the total amount of data that you can send into a given session regarding all the fragments is limited by 8,000 bytes. And from an exploitation point of view, basically you need more session if you want to do more feng shui to actually manipulate the heap and allocate more stuff on the server side. So the more session you have, the more feng shui you can do. And so basically at the end, you can have a more reliable exploit because you have more sessions to spray the memory and have the layout you want. So I was like, okay, that's interesting, because now you can actually exploit larger devices that have more session in a more efficient way, and you can rob from the rich and give to the poor. So I was like, oh, that's cool. I'm just going to call my exploit Robin Hood, because I can pawn the big giant and give to the poor. So my presentation is going to be in 3 steps. First, finding the bug, then triaging the bug, understanding, reversing the bug, and then the 3rd step is going to be exploiting the bug to get code exec. So finding the bug. So this step is quite interesting, because basically I was looking for pre-auth. So I was like, okay, AnyConnect is really cool. I want to know what goes inside SSL. So I use a tool like Burp to just sniff what AnyConnect sends to the ASA. And basically you come up with this simple XML packet, which gives you like the version of AnyConnect and specific other tags to specify specific requirements for the connection. And I was like, oh, that's interesting. That's XML. Because XML is like known, it's like text, so it's easy to read. So I was like, okay, I want to know what are all the tags that are supported on an ASA. So you just take this list of tags, and you just look at Lina, and you start looking at in IDA, and you end up finding this table of basically all the strings corresponding to the tags, with basically a function pointer for each handler. So you have like a handler for each tag. So that's interesting. For now, we don't really care. Here, I actually reversed the whole thing, so I know what field is what. But for now, we don't really care. We just want the list of tags. So we basically build a more complicated initial sample that we can feed to our fuzzer and just try to mutate it and send it to the actual ASA. So it's like an input mutation fuzzing. So the fuzzing architecture I've used is not really complicated, because it's remote. I don't use any instrumentation. I don't it's quite slow. It's really slow. But basically, I call it pray, pray, and pray. The idea, you have your laptop, you have the ASA, and you send a mutated XML packet, so using the full tags. I've used Radamza because it's quite nice for this kind of packet, because it knows the format, so it's going to be still kind of almost valid XML. I don't really care about the response. And then I do a nice CMP ping just to check if the ASA is still alive, because if it crashes, it's going to actually reboot the ASA. So if it's still alive, I don't care, and if it died, I save the thing I've just sent, basically. So I don't do anything complicated. It's really slow. So if you use like AFL, it's like 1,000 test case per second. Me, it's 1 test case per 5 seconds, so it's like really slow. I don't attach any debugger because I don't really need to. I can just save the one that are interested, and then I can replay them later. And at that time, attach a GDB. So the interesting thing is, I wanted to start my fuzzer before going on leave, and at the end, I didn't do it because it kept crashing each time I was sending something. So I was like, whoa. So I basically ran it 2 hours, and then I stopped because otherwise it would have filled my hard disk, right? So I went back from leave, and I was like, okay, I need to triage that. So let's understand. For now, we know we have sent some XML, but the problem is we have 2,000 crashes, and we want to know if they are the same, and we want to know what is the bug. So we've leveraged some tool that we've developed called ASA DBG. So it's basically a wrapper on top of GDB that you can use to debug an ASA that will allow you to sync GDB and IDA using a really good tool called RedSync, developed by Alex Gaze. And basically, leveraging the API from the tool, we are able to connect to the ASA with a GDB. And then we basically fire one of the test case. We get a crash. We save the crash information. And we do that for all of them. And we get basically a bunch of text files, 1 per test case. And now we basically diff them to see if they are the same crasher. So just if you want to do something like that, this is the kind of script I've used in GDB. You can actually define a hook that when GDB hits a stop, like the next time it stops, you can basically define that you want to log something into a text file, then you save the backtrace register, and you continue and you disable logging. And basically, if you execute this script for each test case, you will get like the context for each crash. So the interesting thing is, I had 1 crash, which is kind of expected, right? Because it kept crashing, so it's like something bad is happening all the time, and I'm hitting the same crash over and over. The interesting thing is I was targeting both a real ASA 32-bit and also an ASA virtualized in QEMU. So you have this QEMU output where actually you have an assert being triggered. Not much you can get from that still. So anyway, so now I have at least one. I have the backtrace, and I know they are the same. So I just take the smallest, and I minimized it, like by removing some tags and figure out if it still crashes, and I get this. So this is basically the test case, and the config auth is, well, it doesn't matter. I just give like. I just need them so it's parsed. But what matters is that host scan reply needs to be present. If I remove it, it doesn't crash. So I'm like, okay, that's interesting. Now I have something to work on. The other interesting thing is I actually needed to send this packet twice to trigger a crash. So it's like, okay, that's interesting. For those interested, even though it doesn't really matter for this presentation, host scan is a feature in ASAs where you basically you have this capability for the ASA to say, I just want people having certain configuration to be able to connect. So I'm going to scan the host, like the remote host that tries to connect, to check if they have like an AV or specific requirement. And in this case, what is interested is I'm sending an host scan reply even though I didn't get any request, right? So, I mean, that's just interesting, but yeah. For now, we don't know yet what it is, but if we actually look at the backtrace we get, a few interesting things is we are in a free, so it's trying to free something, and it crashed. We're trying to read a pool type, which is probably a metadata on the heap. So one thing to note is that because we are on Linux, and because they use well-known heap allocators, they basically use either dlmalloc or ptmalloc, depending on the version. They actually use heap metadata on the heap. So one assumption is that we've corrupted a metadata on the heap at some point, and that's why we crashed. But I mean, we don't know if it's a heap overflow, if it's a use after free, double free yet. And the other thing is we are in functions called auth process client request. So it confirms that it's parsing our packets and trying to authenticate us, which makes sense, but it's still good to confirm things when you triage things. Okay, so basically at this point, I started reversing. So basically I spent 2 days just reversing the code around the function that I had identified here to understand what was the bug. And I came up with some functions like aggregate auth parse buff, which basically receive the XML and initialize libexpat to actually parse the XML for you. So it calls libexpat, which is an open source library to parse XML. And the way libexpat works is you can register to libexpat certain callbacks that are called each time certain things are parsed, when they are parsed. So for example, when the XML tag is open, like when it actually parses one XML tag, it will call a callback that you register. And you have specific callbacks that are called like auth start handler, like you can imagine to start the parsing of an XML tag. Then you have auth data handler, which is to actually parse the data inside the XML. And then you have auth end handler, which is to do certain things if you want when it's actually the actual XML tag is closed. So here I had an understanding of what was underneath. But basically, this is the function that actually parsed the data. So that's the one that parsed the actual data of the XML. And the interesting thing is, so the XML tags is the huge table of tags that we saw at the very beginning where all the tags are defined. And so at step 1, basically what happens is you have a special case for host scan reply, where you basically take a pointer in P data, you initialize to a specific pointer, whereas for all other case, you are going to use like a buffer, a global buffer. And then at step 2, what you have is you have a check to check if the actual buffer holds some data. And if it doesn't hold some data, it means previous length is equal to null. And what happens then, if you have, at step 3, you have a check where basically it checks if it had some data. So if we didn't go here, we had some data, we initialized the prev data, we had some data, and what happens is we just append the data in the buffer, and we return, which looks good. So far, yeah, I mean, we don't have any overflow. So far, we're just analyzing it. And then the fourth thing to note is if we didn't go inside this return, meaning we didn't have previous data, so the buffer was empty, what we do is if it was a general case, we initialize the pointer, and if it was the actual host can reply case, we allocate something. So that's why we have two different cases here, because in one case we use a heap buffer, which is 2,000 bytes, and in the other case it uses a buffer, like a global buffer. We don't see it here on the slide, but it uses like a buffer defined on global. So basically, to summarize, we have different cases, and at the end, when it actually finished parsing it, we have a function called to actually free the global pointer. So the interesting here is that if we actually remember that we need to send the packet twice, the first time we send it, it's gonna not have any data. So it's gonna basically go here and allocate something, and it's gonna hold the pointer. At the end, it's gonna free the pointer. And then the next time you call it, because the pointer is still, there is a dangling pointer, here the check here will pass, and even though it's free, it will think there is data, it will append something, and it will return, but it will not allocate anything, so it will copy data into a free chunk, and it will end up calling free again, resulting into a double free vulnerability. So I have just one slide, if you didn't manage to follow the code, that explains from a high-level point of view how this works. So basically, we send the XML packet, the first one. It allocates a 2,000 byte chunk. It's going to copy data in the chunk. Then the chunk is freed. But there is still a dangling pointer retained by the Cisco callback. But the data in that chunk is free, right, in red. I'm just using red to indicate it's free. And then we send the second XML packet. And because of the dangling pointer, it's going to actually append the data in the same chunk, even though it's free. And then it's going to free the same chunk again, resulting into a double free vulnerability. So the interesting thing, just to remember, is that we're working on a 2,000 bytes chunk, which is static for the remaining part. So yeah, just one thing to note is that we have lots of control here because we are able to send one packet, trigger one free, send another packet, trigger the second free, and do everything we want in between. So it looks like a really interesting bug to manipulate the heap and do some feng shui to actually use this double free for something useful. Before we go into exploitation, just to understand why our fuzzer actually found this bug, found the crash. So remember, I was saying the ASA actually used dlmalloc or ptmalloc, depending on the version, but both have a header, metadata for each chunk inlined. And basically the way it is basically you have, if you're familiar with dlmalloc or ptmalloc, you have preffoot and head, which are the two fields specific to dlmalloc or ptmalloc. And then you have, specific to Cisco, you have an additional header, which is actually called mempool header, which is specific to Cisco and holds additional information like who allocated the chunk or specific magic, and even forward and backward pointer. We're going to talk about that. But anyway, here basically we have an allocated chunk, and we have a free chunk, which have different fields. The interesting thing is basically the ref count here for the allocated chunk is at the same offset of a free magic. And basically when you free a chunk, it's going to check the ref count to check that it's less than 11. That's what it does. But basically, in this specific case, because the ref count is actually a magic, it's a lot more, and it's basically check the metadata, check that it's wrong, and it results into an assert being triggered. So that's how we found it, basically, due to the check of the heap, the check of the heap in the free functions. Okay, so now we want to exploit this bug. I said earlier that we're going to leverage iKey to do that. But first, one thing to know about Cisco chunks is that, like I said earlier, you have a specific mempool header in addition to the dlmalloc, ptmalloc header. And you have actually pointers called like forward and backward links, which are part of a linked list. And they use that so they can track all the allocations and track what component allocated what. Basically, from the Cisco shell, you can see that how much memory was taken by iKey, how much memory was taken by SSL, and they basically track all the allocated chunk. If you've done some exploitation on the heap, usually you have linked list pointers on the actual dlmalloc free chunk, but here it's actually an allocated chunk that you have linked list pointers. And the interesting thing about these pointers is you don't have any safe unlinking on these specific pointers. And even though dlmalloc or ptmalloc had safe unlinking on free chunk, because these don't have any safe unlinking, we can abuse them, and if we are able to corrupt them, we can potentially get what we call mirror write primitives, which are basically triggered when you unlink an allocated chunk and free it. So the interesting thing about a mirror write is you have one mirror write, you have one write that is the useful one and the other one that is a side effect. So both need to be writable address. But the interesting thing is we can actually overwrite maybe a pointer or anything in memory where we have the permission, obviously. So this was actually abused in 2016 by Exodus Intel in their iKey exploit already. So what is our strategy? We want to use the double free in WebVPN SSL to create a confusion state on the heap. And the idea is we want to use the confusion state to overflow some memory in order to overwrite the linked list pointers and trigger the mirror writes in order to overwrite a function pointer and then get code execution. So that's the strategy. So I chose to use iKey, so you could argue it's not a good idea. I think it's probably not the best thing to do because basically I require both iKey and SSL to be present. But I just wanted to prove code execution, and I didn't want to spend too much time. So I already know how iKey works, and I know it could be used in different scenarios for the feng shui, and I want to leverage this and learn from it. So I was like, okay, iKey v1, from my experience, is quite reliable. And I know with iKey fragmentation, I'm able to overflow some memory because I can reassemble packets. So the way it works with reassembly, even like without any overflow here, you send different fragments. So each one has a sequence number. And you basically numerate them. And the last one will have a specific flag indicating that it's the last one. And when the ASA receives them all, like it received the last one, it knows that it can reassemble them all, and it basically allocates a large buffer and copy each fragment inside the reassembled packet. And basically this packet, so all these fragments are iKey packets holding a fragment inside, and this packet is like another iKey packet that you need to handle now. So this is the fragmentation. So the interesting thing about fragmentation is that you can easily create holes. So the idea is I'm going to use different colors to explain how I manipulate the heap. And I'm going to use a different color for each session. So here I'm using session 1 in blue in the same session to actually fill all the holes. And I didn't show it before, but I'm assuming at some point I have been able to fill all the holes, so I have some kind of adjacency on the heap. And now I'm using a different session to actually send a fragment that's going to be allocated after the previous one. And then I basically use the same session as before to have another fragment after my red one. Now I send a second fragment from session 2, which has this specific last frag set. The idea being that because we have 2 fragments in this session in red, being sequence number 1 and 2, but this one has the last frag set, the reassembly for this session is going to happen. So it's going to allocate a buffer, and it's going to copy the 2 fragments into this reassemble packet. So in my case, what the data I put actually in the actual fragments, it's completely garbage. So it's at the end, after it has reassembled them all, it's going to throw the packet away because it's not valid IKE packet anyway. But the interesting side effect of this is that it actually created a hole because it used the 2 fragments and it doesn't need this fragment anymore. So it's going to free it, resulting into a hole on the heap. So I have my first primitive, which is I'm able to send fragments in order to create a hole. The second primitive I want to talk about is the overflow one. So just from now on, I'm not going to bother on the slide indicating the different sequence number and last frag bits, but think that all packets are IKE fragments, and they have sequence numbers, so I'm able to reassemble them or manipulate them. So the interesting thing is the bug found by Exodus Intel in 2016 actually was all about IKE fragmentation. And the idea of the bug is that they were able to reduce the accumulated length. So the idea is each time you send a fragment, it's going to actually compute the length of the fragment you just sent, and it's going to store somewhere how much data it has been accumulated, so it knows the length once it received the last one. But the thing is, you could specify a negative length fragment, so you could lie on the actual length of the fragment, and so you could basically reduce the accumulated length, and when the erasable packet was allocated, it would be smaller than the actual size, and when the copy would happen, it would overflow because you had reduced the accumulated length for the erasable packet. It should have been that big, but you managed to arbitrarily reduce it by spoofing the length. So this was the CVE 2016. This was patched. It's not possible to do that anymore. If you specify a negative length fragment, it will just ignore the packet. But the idea I had was to find a way to actually increase a fragment length afterwards. So the idea is I'm going to send fragments of specific size, but if I'm able afterwards to, I'm spoiling, but basically to use the double free to change the length so it's actually larger in memory after it's been received, then because it actually stored the length of the accumulated length of the actual 3 fragments each time it received one, and now I've changed the length in memory, I'm able to allocate a reassemble packet of the supposed to be length, but I will be able to copy more data because I changed the length of the actual fragment in between. So that's what the idea to actually increase the fragment length. So I call it the overflow primitive. So actually, these 2 primitives I've just explained could be applied to any bug. They're quite generic. So actually, this overflow, you would say, okay, if I can arbitrarily increase the size of any fragment, I could increase it a lot, so I could overflow a lot of memory. But actually, in the code, they do check when they actually copy the data, that it doesn't go out of band of the erasable packet? Well, almost. They almost check it because the check is wrong. Because they check that here, so this is the function that reassembled the packet. So it assumes that it has received all the fragments. The first thing it does, it allocates a buffer for the reassemble packet. And the way it does it is it uses a length, which is the accumulated length plus the size of a buffer, which is the buffer holding a pointer for the reassemble packet and some metadata. And then it loops over all the fragments, and it computes the length of the fragment, and then it adds it to the length, and it does a check that the reassemble length doesn't go outside of the actual length. But the problem is the alloc size is actually the accumulated length plus the size of the buffer, and so it doesn't take into account the size of the buffer, meaning we have a capability to actually overflow up to the size of the buffer, even though they do a check. So we have a limited overflow. We are able to overflow up to 18 bytes on 32 bits and a little bit more on 64. But we are able to leverage I-key fragments to overflow data. So the third primitive is related finally to the actual double free vulnerability. So if we assume we have created a hole like before, using the I-key feng shui, what we want basically is to allocate the XML buffer, the 2000 bytes buffer into this hole. And the idea is because it's going to be freed after it's received it, but still keeping a dangling pointer. What we want to achieve is basically to allocate another fragment into this same hole. So here I'm just using a fragment which is a little bit less inside than the actual hole to keep a free chunk. I'm going to explain why. So basically here I have both a dangling pointer for the XML packet and a Nike fragment pointing to the same chunk. Now I trigger my double free primitive, but in this case it's not going to result into a double free because I reallocated something in between, so it's an allocated chunk. But so what happens is it's going to free the I-key fragment, which is what I want. And now what I can do is I can send another fragment from a different session to fill this hole and replace the previous one. And now what I have is I have two I-key fragments into pointing to the same chunk. And I've created like a confusion state. So I can use the red one, but it's going to be actually using the brown one. So this is the repeatable free primitive. I could actually do it over and over, because now I have an allocated chunk again, so I could free it again, but I don't really need to. I have what I want. So it's an interesting confusion state, because it's not like a type confusion bug, but it's confused on the heap. So I have one slide to exploit the whole exploit using the different primitives. So at the bottom, it's the heap. Here it's the actual adjacency I can get by filling all the holes and doing the heap feng shui. And on the right, it's also allocation on the heap, but somewhere else on the heap. And here I'm going to use different sessions to manipulate the heap. So the first thing is I want to fill all the holes using a given sessions, which I named separators in blue. And then I'm using a different session to allocate a chunk adjacent to the previous ones. And I know I'm going to use that green session to create a hole, but for now it's allocated. I'm using another blue one, and then I'm using a different green because it's in different session, but it's going to be to create another hole later. But in this case, I'm using two different fragments because I want to create a larger hole later. And then I'm going to allocate two chunks that are part of two different sessions, which I use orange to indicate that they are going to be the chunks we want to corrupt the linked list pointers to get mirror rights. So for now, I've just been allocating chunks, getting some adjacency. Now I'm sending a fragment to reassemble the first green session So it's going to create a hole. So here I've used 2K chunk because I know the XML is 2K, so I'm doing the feng shui in 2K chunks. I've created a hole of 2K, so now I can trigger my first XML packet, which is going to fit into this hole, and I have a dangling pointer pointing to this hole. Then I'm sending a different session to allocate a chunk into this hole. So I have the dangling pointer and the IKEY first fragment in red pointing to the same chunk. I'm triggering the the repeatable free primitive, which results in freeing the red fragment. And now I'm sending another session in brown to replace the red fragment with another one. So I have a confused red fragment. Now I'm sending the last fragment for the second green session to create a larger hole of 2K. And the idea is I want to reassemble the red session. So I send the last fragment for the red session. And I want it to fit in this hole. So I just make sure the size are so that the reassemble packet will fit into this hole. But because I confuse the red session with a brown one, it's going to actually use this brown and this red to actually fill the hole. But first, it's going to actually allocate a reassemble packet. So I make sure of the size, for the size so it leaves a free chunk afterwards. And here, because it's using the brown one instead of the two red one, it's gonna actually overflow the free chunk afterwards. And I'm able basically to change the size in the metadata of the free chunk from a small value to a large value. So now this reassemble packet is not valid. It's gonna free it, but because it's gonna free a 4K plus a 2K instead of a 4K plus 30, it's gonna result into a 6K buffer, and it's gonna overlap the following chunk. And because I know the size of this chunk, I can send another IKEY chunk, IKEY fragment from a different session to fill this hole and corrupt adjacent chunks. So basically now I have corrupted the metadata of the following chunk. And now, because I control this chunk, I can reassemble the different session and trigger different write primitives to corrupt some function pointer and write some shellcode or trampoline to get code execution. So it's been a little bit quick at the end, but actually, if you want more information, you can look at the way we exploited the IKEY v1 exploit, because basically all the end is exactly the same as on IKEY v1 exploit for the 2016 bug. So a few key facts. The first one is, what is important is that we have the initial session fragment and the one we replace in the same chunk, but we also want this one, the red one, to be a little bit smaller than the brown one. And so here I'm showing the output of some of the tools we've developed to show the chunks called libdlmalloc and libptmalloc, which are open source. But basically, this is the layout of the memory for the red one and the free chunk. We can see it's a malloc and free, allocated and free. And we can see it's a 2K chunk before a free chunk of 10. So this is before the actual memory corruption. And we can see that the actual length of the fragment is 1FE6 in this case. So this is the actual header of the IKEY fragment. And after we corrupt it, we can see we have the same address as before, but we replaced it by a 2K chunk. We have no free chunk afterwards. And here we increase the size of the fragment to be FF2 instead of FE6. And the difference between the two is less than 18 bytes. So that's the first thing. And we have a confusion state between the fact that we have the two fragments in the same chunk. So the second thing is we Hello? Yeah. We leverage the fact that we have an overlapping chunk over chunk we control. And basically, in our example here, we have 6K. But the thing is, for a given session, the total accumulated length, like I said earlier, is limited to 8K. And so one thing about that is, yeah, it's that we have also the constraint for this specific bug that the XML buffer used by the double-free primitive is 2K. And so that's why initially I wanted to use 2K for the feng shui and everything. But the problem with 2K is, like explained here, if we use 2K and 4K for the reassembled packet, the overlapping chunk for 6K will allow you to corrupt 2 targeted chunks. And so you cannot have more than 2 mirror writes primitives, which can be quite limited. So actually the solution is just to change the granularity and to use, for example, 800, because 4 times 800 gives you 2K. And you can basically, if you want a whole of 2K, you can free 4 chunks. And then if you do that, your reassembled packet can be 4K, and you're able to overwrite to get, in this example, 5 mirror writes just using a 4K, whereas we had 2 mirror writes using 6K. So you get more mirror writes. So before doing this, we tried other approaches, which I'm not going to detail here, but I listed them in the slide in case you're interested in. But at the end, it took me 2 weeks to build an exploit for it. But honestly, it was because we had the tools. Prior to that, it took a month to develop the tools to actually leverage the heap, understand how it works and everything. The good thing is, now the tools are available, so if you want to play with this kind of thing, it would take less time. So to conclude here, what do we learn? So the first thing is, even though I've used Radamza to find the bug, in my case, it was useless, because just taking the list of actual XML tags was enough to actually trigger the bug. The other interesting thing is, at the moment, the working exploit is only on 32-bit, where there is no ASLR and depth. If you want to have it working on 64-bit, it requires a little bit more work, because you need to find a remote leak. Even though on some 64-bit that don't have ASLR, you won't have to do that. Another interesting fact is that I kind of looked at triggering the bug on all the different versions, and it's at least 7-year-old bug, and no one found it. So I don't know what you think, but I feel it wasn't really hard to find it. It's not like I had to develop a fuzzer, which is really, really good. I just did like a really basic test. Maybe I was lucky, but I think it shows, even if I was lucky to find it, it showed that nobody actually tried it before. And then the thing is it's in Cisco-specific handlers, so it's not in libexpat. So this bug couldn't apply to other tools using libexpat. And the exploit I've chosen to write leverage IKEv1 to overflow memory, create mirror write primitives. And I think because IKEv1 feng shui is quite reliable, I think it could be used in any other exploit, which could be either IKEv1 or not related. Obviously, as long as IKEv1 is available. Right. So what's next? Well, it would still be nice to have a WebVPN AnyConnect exploit only, not relying on IKEv1. For now, we didn't bother. We just wanted to prove quickly remote code execution. And the thing is, because we have this decorrelation between the two free, we are thinking about ways to actually leverage the double free to actually create a memory relevation primitive. So we have a few ideas. So the idea being to remotely leak some heap content. And because of the Cisco metadata on the heap, they contain some pointers that are both on the heap, but also in the text section, because we have the alloc pointer on chunks. If we're able to get back in response on some packets some content from the heap, we can potentially bypass ASLR and detect the version and build an exploit on the fly. A little bit similar to something like Being Uncertain, which targets Cisco iOS, and the idea of this exploit that was released as part of the leak is to basically send so it's on iOS, so it doesn't work on ASA, and it's patched now. But the idea is you are able to fake the size of a crypto parameter, and because the packet you send is not valid, it's going to send you in response your own packet, so you know what packet was wrong. But because the size you spoof was wrong, you get more data in response. So I had this idea about actually combining something similar to that to the fragmentation, saying if I can have this kind of bug and trigger a fragmentation, which is wrong, I'm going to get more data because the reassembled packet is going to be larger, and in response, I'm going to have more data. Unfortunately, I tried a few things. Even though I was able to get some packet in response, I haven't been able yet to combine both the fragmentation and the packet to get something in response. But if you have any idea to discuss about how to leverage this kind of bug to create a memory relevation primitive, I'm interested to hear about it. Other stuff you could look at is just having a better fuzzer, like XML grammar-based fuzzer, now that that takes into account like tags, attributes, all this kind of thing. Yeah. So to conclude, I think this research, one interesting thing about this is, so we found this bug in October, contacted Cisco, and then because we're doing lots of pen tests, we keep finding we keep encountering Cisco ASA firewalls, and we knew about the bug, but we couldn't really talk about it because it wasn't patched. So we're like trying to think, how can we help our customers protect themselves? And so how do you protect against 0 days? So this is a timeline I drawed to show that the actual Cisco ASA landscape is really different depending on which branch you have. So the way Cisco ASAs are numbers is they use this system of branch where you have 7, 8, whatever, but actually it's a little bit thinking about branch a little bit like Windows versions like XP, Vista, 7, 8. These are actually different branches in the same vein as this could be XP and this could be Windows 10. And they live in parallel, and they are all patched together. So the 9179 is probably going to be released at the same time as the 92414. So they live in parallel. It can be a little bit misleading because they are numbers, but that's really what it is. And so the red one are the ones that are end of life, so you don't want to be in these branches. Like the 9.5 you don't want to be, but the 9.4 you could want to be in 9.4 because it's still patched. But I wouldn't recommend it because in yellow is the one that are still patched, but they don't have like the latest mitigation. So it's interesting because Cisco doesn't actually advertise what branch has what mitigation, but actually it's really interesting to know about it, because if you look at the green one, these are the ones that have both ASLR and depth, so it's a lot better to be in the green one because you have more mitigations. Basically, my current exploit only works on the yellow one, where there is no depth and ASLR, and my exploit doesn't work on the green one. even though it could be improved, but you raise the bar, right? And so basically, to conclude, if you want to protect against 0 days, like if you have a hypothetical 0 day, well, if you want to protect against hypothetical 0 day, I would recommend to be in this branch because you really raise the bar because you need to bypass ASLR and DEP, and it's a lot more difficult. It's like the eternal blue case where you want remotely to bypass ASLR and it's really hard, right? And it's raised the bar. So yeah, so I've been able to exploit this bug because we had developed tools. So I'd like really to thank Aaron, my colleague, to first helping me develop the tools that I actually used to exploit this bug, and also for helping me exploiting this. I also want to thank Terry Grant from the CERT from Cisco for handling this. And if you have any question, I know we don't have much time now, but feel free to ping me either after the conference. I'm here until Sunday, or drop me an email or on Twitter. Thank you very much.
I think we have a couple of minutes for questions.
Thank you for the presentation. Do you know if Cisco added safe unlinking to their heap since?
So I haven't checked like the 9.9, because it's a new branch that has been released, I think, a couple of months ago. Well, actually, yes, it's been released for this bug. But yeah, all the versions I've checked until 9.7, 9.8, they didn't have it. So I'm not aware of anything. The interesting thing is DLmalloc was used for the old version, and they introduced ptmalloc, which has safe unlinking on the actual heap. But because they use their mempool header that doesn't have safe unlinking, there is still a problem. Yeah.
Any other questions?
Are the memory pool headers used for like what corresponds to fast chunks as well, like the small chunks?
Sorry, can you speak louder, please?
Do you know in DLmalloc and ptmalloc you have these fast chunks that are usually like single linked list, even with recent implementations? Or the memory?
Sorry, I don't hear you. Can you just put loud? Yeah.
Okay, sorry.
No, thank you.
In DLmalloc and ptmalloc, you have these fast chunks for small chunks that are only single linked lists when they're freed.
Yeah.
So are the memory pool headers used for those small chunks as well in the Cisco implementation?
So it's so it's only in ptmalloc. So what is your question?
For very small chunks, are they still using the memory pool headers with a double linked list?
Oh, right. Yeah, okay. You're asking for the mempool header. So for the mempool header, the mempool header has a linked list only for allocated chunk, not free chunk. So there is no concept of fast chunk. Or
Okay, good.
But that's a good question.
I think we have time for one more, if anyone has a question. You're close, that's good.
Hi. So, do you know if the Cisco ASA ASLR implementation, how it works under the hood, like what the PRNG is, if there's a potential for like correlation attacks and stuff? Has that been documented?
So they basically use Linux implementation because it's Linux based, and they use a Lina binary, which is one binary with like 30 megs of everything related to Cisco ASA, and it's running in userland as root. But it doesn't really matter, actually, that it runs as root, because when you actually exploit the ASA, all you want is to get the Cisco shell, because then you can do whatever you want because you're an administrator. You don't want to be root. So, but yeah, it just uses the ASLR of the Linux. So each time you boot, your Lina binary will have a different address, so you don't know it in advance.
All right, thanks.
Thank you very much, Cedric.
Thank you.